Have you ever wondered how hot the Earth's core is, or how it's cooling? Let's delve into a deep journey to the heart of our planet, the Earth's core, and its intriguing cooling process. The evolution of Earth is a fascinating tale of gradual cooling. Roughly 4.5 billion years ago, when our planet was in its infancy, the surface was an ocean of magma. Then, as the eons passed, this fiery surface cooled to form what we know as the Earth's outer crust. But the story doesn't end there. Deep beneath our feet, the Earth's core still harbors enormous thermal energy. This heat isn't just sitting idle, it's a dynamic force, driving some of the most incredible processes on our planet. Think about mantle convection, a slow churning of the Earth's mantle caused by heat from the core. This process is akin to a pot of soup simmering on a stove, with hot material rising, cooling, and then sinking again. Then we have plate tectonics, the grand architect of Earth's landscapes. The thermal energy from the core is a significant player here, influencing the movement and interactions of the Earth's tectonic plates. And of course, we cannot forget volcanism, the dramatic and often destructive display of Earth's internal heat. This thermal energy fuels the magma that builds up beneath the surface, eventually leading to volcanic eruptions. Yet even with all these processes, there's still a mystery at the core of our understanding: the rate of the Earth's core cooling. Despite our best efforts, we don't yet know exactly how fast our planet's heart is cooling, or if it will ever cool completely. As we stand on the surface, the Earth beneath our feet may seem solid and unchanging, but deep down it's a different story. The Earth's core is a hotbed of activity, its heat driving processes that shape our world, and it's cooling at a rate we're still trying to understand. So the question remains, at what rate is the Earth's core cooling, and will it ever cool completely? We'll explore more in the next scene. Stay tuned. Enter the researchers at ETH Zurich and their study of a mineral known as bridgmanite. This mineral, bridgmanite, is the unsung hero of our planet's thermal story. Found nestled between the core and the mantle layer of Earth's interior, bridgmanite plays a crucial role in our understanding of the Earth's thermal dynamics. Imagine, if you will, the Earth's core as a gigantic furnace, and the mantle as a shield that keeps the heat from escaping all at once. Right at the interface of these two layers, you'll find bridgmanite. This mineral is essentially the thermometer that gauges the temperature gradient between the fiery core and the cooler mantle. The heat flow from the core to the mantle, and how this flow is conducted, is largely dependent on this extraordinary mineral. But why bridgmanite? Well, the reason lies in its unique location. The boundary layer where bridgmanite is found is a fascinating place. Here, the viscous rock of the Earth's mantle comes into direct contact with the hot iron-nickel melt of the planet's outer core. The temperature gradient between these two layers is very steep, implying a significant amount of heat flow. However, understanding the exact role of bridgmanite is no easy task. Researchers face a daunting challenge in estimating how much heat this mineral conducts from the Earth's core to the mantle. This is because experimental verification is extremely difficult, due to the extreme conditions that prevail inside the Earth. The tremendous pressure and temperature make it impossible to directly observe or measure bridgmanite's heat conduction in its natural environment. But the scientists at ETH Zurich are not deterred. Their study of bridgmanite is pushing the boundaries of our knowledge about the Earth's core and the process of its cooling. By investigating this elusive mineral, the researchers aim to unravel the mysteries of our planet's thermal history and future. In conclusion, the investigation of bridgmanite is vital to understanding the cooling process of Earth's core. It may just hold the key to unlocking the secrets of our planet's thermal evolution, from its fiery beginnings to its potential icy end. The breakthrough came when the researchers developed a unique measuring system. A team of intrepid scientists from ETH Zurich and Carnegie Institution for Science, led by the astute Professor Motohiko Murakami, devised a way to simulate the harsh conditions of Earth's interior, right in the heart of their lab. This was no small feat, as it involved replicating the extreme pressure and temperature conditions that exist thousands of kilometers beneath our feet. Imagine, if you will, the Earth's core, a seething cauldron of molten iron and nickel, under pressure 1,000,000 times more than we experience at sea level, and at temperatures hotter than the surface of the sun. To mimic this environment was a Herculean task, but our brave scientists were up to the challenge. They developed a high-pressure, high-temperature apparatus, a sort of mini-Earth, if you will. Inside this device, they placed a sample of bridgmanite, the most abundant mineral in the Earth's lower mantle. By adjusting the conditions within this apparatus, the researchers were able to measure the thermal conductivity, or heat flow, of bridgmanite under the same conditions that this mineral experiences deep within the Earth. And why is this significant? Well, by understanding how well bridgmanite conducts heat under these conditions, scientists can estimate how much heat is being transferred from the Earth's core to its mantle. This is a crucial piece of the puzzle in understanding the rate at which the Earth's core is cooling. But the genius of their methodology doesn't stop there. You see, they didn't just measure the thermal conductivity of bridgmanite once. They measured it at several different temperatures and pressures, creating a comprehensive picture of how this mineral behaves under a variety of conditions. This allowed them to extrapolate their findings and make more accurate predictions about the cooling rate of the Earth's core. This innovative methodology has opened a new window into understanding the Earth's core cooling process. Through their tireless efforts, these researchers have not only advanced our knowledge of Earth's internal dynamics, but they've also shown us that even the most challenging environments can be recreated and studied right here on the surface. So what does this all mean for Earth's tectonic activities? Well, it's like this. The Earth's core cooling process has significant implications for tectonic activities. You see, the enormous thermal energy emanating from Earth's interior is the driving force behind dynamic processes such as mantle convection, plate tectonics, and volcanism. These processes are responsible for the movement of Earth's crust, causing earthquakes, volcanic eruptions, and the creation of mountain ranges. As the Earth's core cools, the energy supplied to these processes begins to diminish. Over billions of years, the surface of our planet has cooled from a molten state to form the solid crust we live on today. This cooling trend continues, albeit at an incredibly slow pace, deep within the Earth's core. According to the study by Professor Motohiko Murakami and his colleagues, this cooling process can potentially weaken many tectonic activities. The slower the heat conducts from the core to the mantle, the slower the mantle convection will be. The mantle convection is like a massive, slow-churning engine that powers plate tectonics. So if this engine slows down, the tectonic plates' movement will also slow down. This could lead to fewer earthquakes and volcanic eruptions. Sounds great, right? But it's not that simple. While this may sound like a good thing on the surface, these tectonic activities are vital for life as we know it. They play a crucial role in the carbon cycle, which is essential for maintaining Earth's habitable climate. Moreover, the cooling of the Earth's core could also affect Earth's magnetic field, which protects us from harmful solar radiation. The movement of molten iron within Earth's outer core generates this magnetic field. As the core cools, this movement could slow down, potentially weakening our protective shield. Ultimately, the cooling of the Earth's core is not an isolated event. It's a process that's been happening for billions of years and will continue for billions more. It's a process that affects everything from the ground beneath our feet to the air we breathe. The cooling of Earth's core is not just an isolated event, but has far-reaching implications for our planet. But the journey of discovery doesn't end here. As we delve into the intricate study of Earth's core, we are reminded of the remarkable evolution of our planet. 4.5 billion years ago, the surface of our young Earth was swathed in magma. Over the eons, this fiery facade cooled to form the outer crust we now inhabit. We've learned that bridgmanite, a mineral found at the boundary layer between the core and mantle of Earth's interior, plays a significant role in this cooling process. The steep temperature gradient at this boundary means potentially significant heat flow. Yet, until now, estimating how much heat bridgmanite conducts from the Earth's core to the mantle has been a perilous puzzle. Thanks to the diligent work of Professor Motohiko Murakami and his team at ETH Zurich and the Carnegie Institution for Science, we now have a method to measure the thermal conductivity of bridgmanite under the very conditions that prevail inside the Earth. This is a significant step forward in our understanding of the Earth's core and its cooling process. The study also suggests that the core cooling can affect tectonic activities. This could have profound implications for our understanding of seismic events, plate tectonics, and volcanic activities. As our planet continues to evolve, so too will our knowledge of its dynamic processes. Yet the question remains, at what rate is Earth's core cooling, and will it cool down completely? The answers to these questions hold the keys to unlocking further secrets of our planet's past, present, and future. The importance of continued research in this area cannot be overstated. As we deepen our understanding of the Earth's core, we stand on the precipice of potential new discoveries that could revolutionize our comprehension of our planet and its place in the cosmos. As we continue to explore the mysteries of our planet, who knows what we'll uncover next?